All right, before we get to the specific questions on this study guide, just a couple of general things to, if you remembered all this general stuff, hopefully most of this wasn't too difficult. What are 3 ways to accelerate? First thing we discussed yesterday, three ways. Go ahead, Brady. Good. Basically, speed up, slow down, change direction. All right. What is fill in the blank of the word definition for acceleration? Those are the 3 ways. But the reason why those are the 3 ways is because how acceleration is defined. And acceleration is a change in blank over time. What am I talking about? Yeah. Velocity over time. And since speeding up changes your velocity, right? Since slowing down changes your velocity, and since velocity is a vector, changing direction even all by itself would also change your velocity, right? So that's why those are the 3 ways, by definition, to accelerate. What did we say was the most common unit we'll use? Not the only one we run into, but metrically, the most common unit we'll see on accelerations. Especially when we leave this intro stuff, I don't think you'll ever see an acceleration that's not this value, this type of value. Go ahead. Good, meters per second squared. What's another way we could write that means the same thing that's less condensed? Go ahead. Meters per second per second. And saying it that way really tells you what it's about. Like, per any time unit, you speed up by this much. And there's some questions based on that to review that idea that we went over. And all that stuff's important right there, but maybe the most important thing is what we kind of ended class yesterday with a lot of examples of me walking one way or the other. The fact that if, I could ask this a couple different ways. So if I tell you a positive acceleration, does that guarantee that the thing's speeding up? No, because you have to know what direction the thing was going in the first place. All right? Remember, there was basically, we're still in 1D motion, so there's only 4 options. All right? Either you have a positive velocity with a positive acceleration, plus means speed up. Or a negative velocity with a negative acceleration. Negative still means speed up. All right? The V and the A at the given moment are both the same sign. It means speeding up. Just alone knowing the direction of acceleration, that's not a valid question to ask. Because you don't know unless you knew to see it or just told which way was it going in the first place. And then if they're opposite, if you have a positive direction V and a negative direction A, then you're doing what? Only one other choice. If you're going in the positive direction, but a negative acceleration's on you, if those oppose, then what are you doing? Not speeding up, but slowing down. We could flip-flop that. I could be going in a negative direction and have a positive acceleration. Negative, positive, 2 opposite signs, slowing down. The whole backside of this were questions on that idea. They just might not have used positive, negative the whole time. We could use other directions as well that are stated that are on the same axis, right? So we'll review that more with the backside questions. But all that's like the core stuff on acceleration. And by the way, we're not going to worry about it till later, but we said it and just keeping it in mind. What is it that causes accelerations? They don't just magically happen. Yeah. Forces. And for all you're concerned right now, force is just any push or pull. All right? But that's not going to be any focus of anything current right now. But we might as well say it. Accelerations just can't magically happen. There's going to be forces that cause it. And that's essentially one of Newton's laws. We'll word it in a more specific way later. Okay, so with all that stuff in mind, and number 1, it basically says, give us 3 controls in a vehicle that can cause the 3 different ways you could possibly accelerate. So this should be pretty common sense, right? What's one? Go ahead, sir. Gas pedal. When you hit the gas pedal, you speed up, right? What's another one? Brake pedal. When we hit the brakes, you slow down. And what's the final one, Braden? The steering wheel, because when we move the steering wheel, we turn, right? So just all 3 ways could occur in something like a vehicle. In most moving things, there's something that could cause all 3 of those. But a vehicle is pretty familiar to us. Number 2. I think this may have been the first study guide we had that had like the circle all that could apply. Just be careful. That means there could be more than one right answer, but there doesn't have to be. I'm not going to ask questions like that on my multiple choice one. The multiple choice ones I give you on my quiz on Friday, there's only going to be one right answer, okay? But there are two on this one. So an object is accelerating if it is moving blank. Circle all that applies. As long as we are keeping in mind those three ways to accelerate. Changing speed, absolutely, right? Changing speed could cover both of those first two types, right? You could speed up or slow down. That would be changing either one of them. So you're definitely accelerating. And choice D is a correct answer as well, because if you're moving in a circle, you're constantly changing what? Direction, and that was the third type. We will eventually have a topic that's its own chapter called circular motion. Uniform circular motion, actually, but we'll focus on that more. But before we move on to the next question, there's a very common year after year incorrect one I get on this one. So I want to point it out because I'm sure there's probably a few people out there. I'm not going to ask you to raise your hand if you got this wrong, but if you chose extremely fast as an answer to this one, because year after year I get a lot of that. That's not correct. Why is the fact of just knowing you're moving extremely fast wouldn't be guaranteed acceleration? Yes. Well, if you're moving fast, you got to be going somewhere, right? Yeah, you can't have motion without going anywhere. So, what do you think that, Dave? Exactly. Going extremely fast, that could mean that you're just going at a really fast constant velocity, right? And if your velocity is constant, then that's the exact opposite to the definition of acceleration, right? Acceleration is a changing velocity over time, right? And if your velocity is constant, it's sure not changing. So you could be like light. Light in a vacuum coming through space from the sun right now is going 300 million meters per second. But if it's just in space, not going through something else, into something else, it's just going extremely fast. It's not accelerating. Now, once it hits our atmosphere, we'll learn with some stuff way late in the year with waves, it will immediately slow it down to a much slower speed. Or if it goes through the glass right there. While it's in there, it's slowing it down. But just because something's moving extremely fast doesn't mean it's got to be accelerating. Could be, but it doesn't have to be, so that's why it's not one of the answers. All right, number 3, be careful with this one because of what it says right here. For sure, okay? If an object is not accelerating, if we're telling you something is not accelerating, it says then we know for sure, 100%, not maybe, 100%, that it is what? A lot of the wrong answers I get on this one is at rest. At rest, you are not accelerating at rest, but that's not just what it said, for sure, right? So, if I just tell you something's not accelerating, if you don't see it, there's something out in the hallway right now that's not accelerating that you can't see. Does that guarantee 100% it's at rest? No, because it could be traveling how? A constant velocity. We'll be a little more specific there. A constant velocity, right? So if we don't know 100% for sure, we can't answer with it. Slowing down is clearly acceleration, so that can't be the right answer, right? So these two are both valid. If we know something's not accelerating, then its speed can't be changing, right? Its speed, its magnitude of whatever it is. That might even be 0. If something is at rest, and we're not saying it has to be, but if it is, that's still a constant speed, isn't it? A constant speed of 0 is still a constant speed. So if something's not accelerating, I can guarantee you 100% sure that it's moving with a constant speed. That speed's not changing. And we could go a little further. We could answer it a little further and say that same statement with velocity. Because if it's not accelerating, the direction can't be changing either, right? Velocity is a vector, and if it's constant, that wouldn't change. So B and D would fit the for sure parts on that one. Any questions on those? All right, then we gave this little formula, right? And we came upon this little symbol. Now, the name of it's delta, but that's just the Greek symbol. What did we say the delta symbol in the formula means, Ethan? Change in. Or in other words, a later thing minus an earlier thing. A final minus an initial. Now, I did warn you that this calls it original, not initial. And and you'll more commonly see it called initial. But original means the same thing, okay? So this delta V, or delta velocity, means final velocity, or usually just VF, minus initial velocity, VI. or original means the same thing. So that's the expanded version. That's the condensed version. Still both divided by time. Again, next week when we get into motion graphing, you'll see where this equation originated from graphs and data, okay? For now, we're just slapping at you like here it is, but it came from somewhere. So for especially some of the last couple down here, we'll have to apply that. The first few questions really, as long as you know the idea of acceleration, you don't need this formula for. These are more like conceptual questions on the idea of at least these two, 4 and 5. So number 4, an object with an acceleration of 10 meters per second squared will circle all that apply. Remember, just because it says circle all that apply, there could be more than one answer, but there could just still be one, and there is only one. The only thing that matters there, if we understand the unit, like we said it broken apart a moment ago and yesterday, meters per second squared can be said how again? Another way to say that, in a less condensed mathematical version of it, was what? Meters per second per second. Just say those units and think about what they mean. That whatever the magnitude is, 10, right? Now, were we told if this thing was speeding up or slowing down? No. So, at best, we could say it changes its velocity. There's two ways to change velocity through magnitude, speed up or slow down, right? But either way, it would be changing it by 10 meters per second every second. We gave an example similar to that yesterday. If I say something has this nice uniform acceleration of 10 meters per second squared, every second that goes by, your speed decreases by 10 meters per second. So if 2 seconds go by, you're at 20. If 3 seconds, you're at 30. Easy, simple pattern, right? That's what it means. Choice B. None of the other ones. Another common wrong answer, and I can see why a lot of us could pick this one. D doesn't have to be a correct. Anywhere in the actual question or statement, did it ever say the thing started from rest? Did it ever tell us that? No. If you assume that, which you shouldn't, then choice D would be correct, wouldn't it, based on that pattern? If you started at 0 seconds at 0 speed, right, from rest, wouldn't if you increase by 10 for 10 seconds, you'd be up to 100? All right, so if anybody put that one, you're close. Your thinking's along the right track, but since it never told me I started at from rest, that doesn't have to be true, does it? All right, the only thing that has to be true is that we're changing our velocity by 10 meters per second every second. In number 5, it gives us that pattern stretched out again. And elementary pattern should be able to easily catch on to it using the units given. So this person increases, or in other words, speeds up from rest. That means at 0 seconds, we're going 0 miles per hour. That means we started from rest. And then 1 second later, we're at 10 miles per hour. 2 seconds later, we're at 20 miles per hour. 3 seconds later, 30, and so on. The pattern's obvious. Every second, I'm speeding up by how much? Ethan? 10 miles per hour. So my acceleration rate is 10 miles per hour per second. Make sense? All right. Now we get into using the formula a little bit. This formula is only going to be used for this week. Well, it's going to be used a lot. But while we use it this week, we're only going to use it straightforward. So what I'm saying is you only have to use it to solve for acceleration. But not too far from now, you will have to rearrange this one algebraically, but not for this week. So we just got to plug in. Yes? Where? Okay, because, right there? Okay, because, now if it was per second, seconds and seconds are like units, right? So you could, a second in a second is a second squared, right? But since we left this in hours, because it didn't tell us we had to convert it, so hours and seconds are 2 different units, right? So they can't condense into something squared. Now, if you really wanted to, you didn't have to, if you really wanted to, you could convert all, it would actually be the easiest to do it early. You could convert all these hours in each one of these units to seconds, and that would change those numbers, though. And that would have a different number here in miles per second squared. Don't worry, you don't have to do that, okay? But that's why we can't condense those two together. When the per time unit involved in the acceleration are the same time unit, you could condense them into the squared unit in the denominator. Does that answer your question? Okay. All right, so anyways, back to this simple little formula. Yes, you are responsible for when we use V equals D over T the other day, the only other formula we really have. Average speed equals distance over time, average velocity equals displacement over time. We did have some problems where we had a very simple algebra rearrangement of that formula, right? Since we did that on one of the study guides, you might have to do that on the quiz, but not for this equation yet. This equation eventually in a couple weeks is going to have 3 more equations in a group. We're going to call it kinematic equations. And you will have to rearrange them all as needed algebraically. We'll worry about that then. For now, you're using it straight up for acceleration only this week. So we're saying a force accelerates from 0 to 60 miles per hour in 4 seconds. Its acceleration is, the correct answer is C, but the reason why is 60 is the final velocity. That's what we got up to, right? So 60 goes in for V final. 0 means it started from rest. We put that in for V original. Divided by the time it took 4 seconds, we run those numbers. It will be 15 miles per hour per second based on the given units. Make sense? Similar with these ones. This one literally says starts from rest. This should go without saying, but if I don't say it, somebody out there might not get it. When we say something starts from rest, what's your initial velocity? Yes, 0. Although it doesn't say it in this one, on the flip side, if something comes to a stop, final velocity is what? 0. So watch out for just words that tell you things are 0, basically. So from rest means V original or V initial 0. 0 goes there. Gets up to positive 16. 16 goes there in 4 seconds. Run those numbers through that formula, and you get 4 meters per second squared. Since that was in meters per second, that was in seconds, we would get meters per second when we plug it into the math with the division. And then you can condense it into meters per second squared. All right? And finally, another one. A car slows down. Now, I know we can see the answer there, and we all solved it anyway by now. But notice, this one does clearly say I'm slowing down, right? And as I'm slowing down the whole time, what direction am I staying in? The what direction, based on these numbers? Right there. As I'm slowing down, I'm going in what direction? Positive. So we should know from that little thing we went over yesterday. If I'm going in the positive direction and slowing down, when I could predict even before plugging in the numbers in this formula. I should be able to predict what kind of answer am I going to get out from acceleration. That will make sense. Negative, right? If I'm going positive and I'm slowing down, I'd better get out of negative. If you know your concepts well throughout this whole year for all kind of calculations, if you know the idea well, you could check a lot of your answers just to see if it makes common sense based on the situation. Like if I know that's supposed to happen, if I'm 100% sure of that concept, and I run the math and I get out a positive acceleration, I know I did something wrong. I probably made a dumb math mistake. Now, you could use that as a general check to see if it just makes sense to what we're trying to learn. So when we plug in these numbers, 32 is the V original, or initial. 8's the final, because we get to that, divided by 4, and that's going to be negative 6 meters per second squared. And trust me, when the formulas get harder, past this early stuff, we will break down and I will show all the work when I go over it. Right now, it's still a pretty simple equation to plug in. I'm not going to waste our time by showing every little step to these tiny little equations. When they get bigger, we will do that, okay? Any questions on anything on the front side of this? All right. On the back, just continues with that idea. And I understand if you got confused on number 10 because the diagram isn't drawn the best. But once you understand the diagram, it should be a pretty easy one, okay? But first, along the same lines, a similar idea with this whole sign stuff we just talked about on that last problem. All right? Just keep remembering, if you're slowing down, the signs of your V and A have to be opposite. The directions of your V and A have to be opposite. If you're speeding up, they have to be the same. If you remember that, these should be crazy easy questions. So in letter A, the car is moving eastward along Lake Avenue and is increasing its speed. So it's telling me it's speeding up. From 25 to 45. What would be the direction of the acceleration? We don't have enough information to actually find it as a whole number. We just want the direction. So if I'm moving east and speeding up, then the acceleration has to be what, guys? Okay. What? Or use what we're saying. Since we're using east and west, use that. So eastward, right? Same. If we're speeding up, same, right? If we're slowing down, opposites. Or whatever the direction used. So actually, I believe B to G on this are all slowing down now. That was the only speeding up one. So the answers to all of those, we'll still go over each one individually, but the answer to all of these are going to be opposite of the other direction because they're all speeding down. So a northbound car skids to a stop. If I'm going north and skidding to a stop, my acceleration's got to be southbound because the acceleration is caused by a force. When you're in your car, what's going to stop your car? Your brakes, right? Hopefully. You're not hitting something else. But when you hit your brakes, you apply an opposing force through the contact of your tires in the road. And that opposing force is friction. And it tries to go opposite of the direction you're moving to slow you down, right? This makes common sense. If you want to slow down, you don't apply a force and acceleration in the same direction you're going. That would speed you up, right? So that's the whole thinking behind here. And letter C, an Olympic diver slows down by splashing into the water below. You hit the water. You're moving down, right? As you slow down, therefore the water is accelerating you upward by pushing back on you. And water actually gets into something, if there's time, way later in the year, we'll discuss floating and the buoyant force and how exactly all of that works. Letter D, a southbound, that's a typo, by the way. That should be free kick delivered by the opposing team. It's slowed down and stopped by the goalie. So if it's going south and slowing down, then the acceleration's got to be north. And just to speed it up a little bit, because I want to show that video at the end, for the same reason, these ones are all the opposite, because all these ones are slowing down. Make sense? All right. Now for this one, a couple things. I know it was running late in class when I assigned this. Did I tell your class not to worry about giving a reason on these ones? Okay. There's barely any space there, right? All I care is about these answers right here. All right, right word, left word, because the reason's for the same reason as everything above. If you put in a reason, I don't care. That's great. I'm not going to be because I didn't tell you not to. But here's the deal. Here's what I think confuses people about this one. The idea is this is supposed to be a ramp that's like propped up on something, like this thing. This is a ramp propped up on this table, essentially, now, right? We're going to roll a car down this ramp, and I know this picture didn't do the best at seeing that since it was a 2D picture trying to represent a 3D situation. Right? But this is supposed to just be that ramp. Then, somewhere on the floor, like right here, this ramp just has a track to it that this car that's rolled down can go around, flat on the floor. Does that make sense? And there's three positions we're going to ask about. Position X, Y, and Z as the car passes those points. But I'm actually even going to change the answer because of the situation on the ramp at position X. I don't think it makes the most sense to use right word. Because when you're going on a ramp, which way are you going? When you're rolling down it? I just said it. Down, right? If you use right, that's fine, but I think it's more sense on the ramp to say down. So if I just let anything, it doesn't have to be hard to be a marble or something, all right? So when you roll down this thing, its velocity at point X would definitely go down, right? If it's rolling freely down it, is it speeding up or slowing down? Common sense. Yes. Speeding up. So if I'm rolling downward, I would put down right here to make more sense of what I'm saying. And then acceleration would have to be what as well? Down. Down, down means speeding up, right? And that's what would be happening at position X. Right's fine too, but I think it makes more sense for down, down. Now we're on the ground, so right and left makes sense here. This is just a flat track on the ground once it gets to the bottom, but it says something over here that tells me once I get to here, to the end, from here to here, I slow down. And that would really happen if you had a toy car on a track. Because friction again. Something we'll learn a lot more about later, but it would slow down because of friction. All that matters now is that it's slowing down. At position Y, as I move, I'm going to move around the track. If my laser pointers, the car would go around like that, right? So at position Y, my velocity is going which direction right here? Position Y, I'm going what direction, guys? Yes. Going to the right, and if I'm slowing down, because it told me that, acceleration would be to the left. And then the curve in the track redirects me, which is just going to reverse everything. I'm still slowing down until I get to the end, right? But as I go through position Z, now I'm going to the left, so my acceleration has to be right, because it redirected everything to turn, right? Same idea as up here, but it was a little more confusing maybe because of the diagram. But the idea should be still simple as long as you understand that. Any questions anywhere on this thing? All right, I'm just going to play that Crash Course Physics video.